explosion of a Type II supernova showers the universe with heavy elements. The core of the exploding star is left intact. Destroying that is gravity's job. But to crush the core any smaller than the size of a white dwarf, it will have to overcome that strange force, electron degeneracy pressure.
Gravity actually finds a way of defeating that tendency the electrons have to push each other apart by combining the electrons with the protons and turning them into neutrons. You now have an object which is made almost entirely out of neutrons, and gravity wins. It now allows the system to collapse further. There are no longer electrons stopping that, and gravity seems to win, except neutrons, it turns out, also don't like each other, and you end up with a new stable object, even smaller, even more dense, called a neutron star.
Compared to normal stars, neutron stars are cosmic pebbles. They can be as small as 10 miles across.
So imagine you take a star about 1.5 times the size of our sun, and then you compress all of that material down into a very small space, about the size of Manhattan. You've just made yourself a neutron star.
Squeezing that amount of mass into such a small space makes for an extremely dense object. 1 teaspoonful of neutron star material would weigh 1 billion tons.
Neutron stars are some of the most exciting and weird objects in the universe that astronomers study. If a human being were to stand on a neutron star, it would be a somewhat uncomfortable experience. On Earth, if they weighed about 150 pounds, on a neutron star, they would weigh something like 10 billion tons. Our biology can't stand that amount of pressure, and so a human being would essentially be squashed flat against the surface of the star. In addition to that, neutron stars are spinning at an incredibly high rate, hundreds of times per second in some cases.
It's this rapid spin that enabled astronomers to first identify neutron stars.
Some neutron stars are spinning really rapidly, and they have a really amazingly high magnetic field. That magnetic field, together with the spin, forces a bunch of charged particles, electrons, to go along the axis of the magnetic field. And those accelerated electrons give off light. They produce a well-focused beam of light. Now, this is like a lighthouse whose beam is always on, but you only see it when the lighthouse beam intersects your line of sight. In a similar way, we might see the shining neutron star only when the beam points at us. That object is called a pulsar.
Some stars are so massive, perhaps 25 or 40 times the mass of the Sun, that not even a neutron star can hold up under the weight of their collapse. And gravity will crush them even further into an object of infinite density and almost equally limitless fascination, a black hole.
In some sense, a black hole represents the ultimate death of a star.
A black hole is basically gravity's victory over mass. It is complete collapse of a star, a very massive star.
This collapse creates a region of space where matter is compressed into such a high density that its gravitational field is inescapable.